Hello and welcome to Toddcast number 65. We're winding down this collection of Toddcasts. And so I believe in the very beginning, I said there'd be 67. Ends up I consolidated two along the way into one Toddcast. So we're going to make it to 66 for what amounts to first semester organic chemistry in a course I would be teaching. Now, if you're using these to review after the fact, going back to OChem, you probably don't really care what's first semester, second semester, you're just looking for topics. But this in the next podcast, 66, will end the ketone and aldehyde starting material reactions and thrust us forward into what becomes a much more synthesis-driven organic chemistry experience. So we're starting to get enough reactions. So with just alkenes and alkynes and SO1, SN2, we didn't necessarily have um, an exorbitant amount of information, but we could build different molecules and have some multi-step synthetic pathways. But once we add in all these carbonyl reactions, and in particular, the Wittig we'll do in this podcast, and the Bear Villager, which we'll do in the next podcast, you get a pool of reactivity that actually becomes pretty substantial to build a good number of molecules. And then future podcasts, which will correspond with second semester organic chemistry, will have more complex carbonyl compounds. So we'll do a lot more with the alpha proton and using that as a nucleophile. And I mean, honestly, before long, it becomes absolutely overwhelming to the point where there are multi-page or like multi book books, if you will, part A, B, C, etc., on just reaction chemistry. I mean, there's literally, if you go to grad school, several thousand plus page books of just reaction after reaction after reaction. And so we twist and mix things up enough and make fine-tuned changes. We're going to see that with the Wittig reaction. Now, the simple reaction has been modified, distorted, twisted, whatever verb you want to use, into several different versions of it, all for very specific targeted needs in one synthesis. And so that's kind of what chemistry becomes. So we're still on foundation reactions, but know that you have reached a threshold where you can start looking at twisted variation. So you design a molecule ever so slightly with a slightly bulkier group on one side to enhance its steric hindrance in a transition state. Or you add an electron donating withdrawing group to enhance the electron richness or electron poorness of an intermediate in a reaction, which will facilitate certain types of pathways to occur. And so it gets complex pretty quick. So do yourself a favor and keep a very, very thorough list of reactions, but now add more caveats of little changes and little twists that we can do to them. So with that in mind, let me go ahead and get into the core of this. I'm going to start with the Wolff-Kishner. And we looked at it real briefly when we were looking at reductions a few podcasts back. And what it was is one where you could actually completely get rid of the carbonyl and turn it into a pair of H's, meaning you could convert a ketone or an aldehyde into an alkane. We used this molecule once already, hydrazine. So hydrazine is simply two H's on an N bonded to another N, which has two H's. So it's two NH2s stuck together. It's a symmetric molecule. Doesn't matter which N is which here, just one of them will react with this. And it's pretty much just us using our magic water box yet again. So here's hydrazine, that reactant, and the derivative of the ketone is known as a hydrazone. And so when you start doing sugar chemistry, you'll run into something called a phenylhydrazone, which is something that binds to a carbonyl on a sugar and helps you identify what the sugar is. But hydrazine is going to react with a ketone in this case, and you have to push a reaction uphill, hence the fairly high temperature, and then ultimately you're going to deprotonate it to get down to the alkene. And the other molecule that's coming off. So in the first one, hopefully you'll identify the fact that two H's on the hydrazine will interact with one O in the water. And then if you look at the rest of it, the KOH, two KOHs are going to come in. The OH minuses are going to pick up H's. And you're going to end up with H's here as well. So those two H's ultimately are going to move there, but not directly. These two H's will move to OH minuses, and then The two H's ending up here come from water to regenerate OH minus, and your side product is going to be N2. So somehow, some way, we're going to have to generate N2. Very, very stable side product. So that's the driving force of the reaction, the generation of a highly stable N2 molecule. So here we go. So first things first, how do you generate this compound? So this is your hydrazine. We've gone through this mechanism a little bit, but long story, under acidic or basic conditions, here we have it acidic. We'll protonate the O. The N will come as a nucleophile, break the pi bond, form the new bond. And so we'll, along the way, get an intermediate that will look like this. After one round of protonate, break, make, deprotonate. The H has an O. This N has an H. And we have an NH2. Okay. Then, after one more round, so again, protonate, break the pi bond, make the N, deprotonate the H. A second round will involve protonate, break, make, deprotonate. So 2 rounds of protonate, break, make, deprotonate by way of this intermediate here. And we have this this hydrazine, or hydrazone, excuse me, hydrazine bound to the carbonyl for hydrazone. Okay, so the catalytic acid helps put this on. We then isolate this compound, and it's on to step 2. Step 2, strong base, again, high temperature, doing this in water. We're going to throw OH minus in. OH minus is going to take the most acidic proton, which is on N as opposed to carbon. We need a high temperature because it just isn't very acidic. So to make this react, we need to push it uphill. The OH minus will come and take the H. Those electrons will come in and sit on that nitrogen. So you end up now with an anionic nitrogen. Let me erase the intermediate structure. So again, I want to say in a previous podcast, we covered this transformation already. So now I'm picking up at the hydrazone and going forward. This negative charge can resonate over to an NN double bond and move electrons to that carbon. Make that carbon negatively charged, and so it can interact with water. It's an aqueous solution. That negative can come pick up an H, and you regenerate the OH minus. So deprotonate, make, break, protonate. Let me just mark those steps. Deprotonate, because it's in base, so we deprotonate first. Make, break, protonate. Okay, we're only halfway there. We only have one H added and one H removed, so on the next round. So we take the syn compound, we once again deprotonate, putting a negative on that N. That can resonate in, so we can make and break bonds. Come with an anion. N2 is such a stable molecule as a leaving group, it's gone. Last step then, protonate. Let me draw my P in a different spot. Protonate, no pair is going to come and attack. You're going to end up with your final compound. So you can convert a ketone into an alkane. Alkanes are rather inert, so this seems like a strange thing to do. So a straight ketone, probably not. But if I had a large molecule where I wanted to get rid of one of the carbonyls on it, but I want to leave everything else intact, then under these basic conditions, I can ultimately convert hydrazone into an alkane. Okay, keep in mind this is catalytic acid, so although this is acidic in nature, excuse me, it can be done at a relatively mild pH. So if you have an acid-sensitive compound on the rest of the molecule, you still are probably going to be okay. It's not enough acid to really make a difference. Okay, that's the Wolff-Kishner. Wolff-Kishner gets rid of a carbonyl when you don't want one. The Wittig reaction. The Wittig reaction is huge. The Wittig reaction opened up a whole new set of doors because up to this point, Grignard is the only carbon-carbon bond-making reaction we really know. We can add an alkyne as a nucleophile, but contrary to how easy it looks on paper, it's a little more challenging to do than meets the eye. So we do have the alkyne nucleophile, we have a cyanonucleophile, but Grignard was really the main staple of the new carbon-carbon bond forming reactions. So Wittig is a way to make a new carbon to carbon double bond. So you'll notice this group is here, this group is here, which means oxygen must be binding phosphorus, which it does. Phosphorus is said to be oxophilic, meaning it forms very stable interactions with oxygen. Once it forms them, it's done. So if you think about the fact phosphate is incredibly stable, you know that phosphorus has a higher affinity for oxygen than it does for carbon. So the driving force in this reaction isn't necessarily the desire to make a carbon-carbon bond, but instead for phosphorus to make a bond oxygen rather than carbon. So the chemistry, although we're doing organic chemistry and making carbon-carbon bond, has a certain element of inorganic chemistry, the phosphorus interacting with the O as our driving force. So once historically they realized that the phosphorus being the O was the more important feature, they started modifying the phosphate portion, the phosphorus portion, to change the reactivity they needed. They went less to less focus on the carbon, the groups on there, to more focus on the phosphorus. And kind of an interesting twist when somebody takes things and looks at it ever so slightly differently. So when you're organic centric, you do what I did. You draw the two circles around the carbon species, show where they are, and you ignore everything else. For people who think a little more broadly, they think about the other things and see how they impact what they're interested in and see if you can modify here or here. And sure enough, we can. Okay, this reactant is somewhere in a, I don't know, resonance hybrid between the carbon phosphorus double bond where you have a pentavalent phosphorus. So that's has an expanded octet, it can do it, but benzene rings, phenyl groups are so huge that there's a certain crowdedness that this bond doesn't want to be as short as needed for a double bond. So it actually has a reasonable resonance contributor where this carbon carries a negative charge. It's big enough that this carbon is actually borderline anionic. So this is high enough, or I guess a major enough contributor. This is your major, this is your minor, but it is close enough to equal that you start seeing a distinct negative behavior of that carbon. So very similar to the Grignard, you make a carbon nucleophile. So when a ketone, or just a carbonyl of some sort, gets near this compound, this negative carbon wants to join with the positive carbon. And we already know an oxygen wants to join with phosphorus. So as those two get closer together, you're going to start seeing that interaction. O is going to start interacting with phosphorus. Carbon's going to interact with carbon. And when this happens, you have this Wittig transition state, this four-centered transition state where oxygen is starting to bond to phosphorus. The phosphorus carbon pi bond, which is vague to begin with anyway, is disappearing. Carbon-carbon sigma bond starts to come into play, and the carbon-oxygen bond that can break due to resonance is disappearing. Okay. Then, once completed, it can move over. So that seems reasonable. So that four-centered transition state. But it can go even one step further. So this four-centered transition state can actually now become the second bond to O can move over to phosphorus. Second bond from phosphorus to carbon can turn and become a carbon-carbon bond. And so somewhere between a sigma pi resonance here and a pi bond here, and this four-centered transition state to the breaking of the two sigma bonds here and the forming of a pi bond here, you have this flow of electrons around the system. So these are going to go there, that goes there, kind of like it did before. So you get this electron flow, and you have these two molecules that notice the atoms in the same spot as they are here. Everything's in the way, so there's a lot of steric hindrance going in here. Really want to emphasize the fact that there's crowdedness that will impact how these things align. But most importantly, you now have the phosphorus and oxygen happy, and you have a carbon-carbon bond that formed by default. Once those bonds are formed, two molecules are free to move apart from one another, and you have your isolated alkene that we synthesized, and the phosphorus with an oxygen bond to it, so the happy phosphorus. Okay, so this reaction, again, revolutionary at the time, studied and manipulated and twisted so many times that you could literally write an entire chapter in a synthesis textbook on just the Wittig and the Wittig variations. Okay, so stereoselectivity. You want to first consider the phosphorus species we make. So we take the phosphorus, we add it to, in this case, a primary alkyl iodide, the nucleophile, very good nucleophile, one of the best, comes in and kicks out the iodide. And so we have the phospholipid where this is that species we made earlier, except it still has three H's, have the I minus. So it's an SN2 reaction one we're very familiar with. The I minus is complexing here and holding place. And it ends up that if we add a strong enough base, N-butyl lithium, it can pull this H off, or this H, either one, and turn it into a true phospholipid. So now this is free to form the phosphorus carbon double bond. So we do an SN2 with triphenylphosphine, followed by strong base, bully. So we use N-bully. We could use T-bully, but bully, we remove it, end up with this compound. So we now have our Wittig reagent. Once synthesized, and again, this is an equilibrium, we're ready to add it to our carbonyl. So let's say we add it to this aldehyde. So I'm going to use benzaldehyde. Note that on the carbonyl, there is a benzene ring and an H, something tiny and something bulky. There is a CH3 and an H, so something tiny and something mid-size. When I mix them together, you actually get trans orientation of the H in the phenyl ring, not the cis that they kind of allude to on this one. So the H's are cis, the methyl and the phenyl are cis to one another. But it seems like the crowdedness would be an issue here, which means the driving force in this case probably is orbital overlap, and alignment of the phosphorus oxygen is more important than the crowdedness. So at least in this case, we get the major product being cis, the two bulkiest group on the same side. Same side cis. So it's fine. Then when we resort to something that's electron withdrawing, so an electron withdrawing group here, and so my prediction or my first thought was steric hindrance would play a big role, but clearly it didn't. So it must have been orbital interactions. Good way to test if it is orbital interactions, and this is one of the first things they did. They went ahead and added an electron withdrawing group. So an ester has a C double bond O, which can withdraw by resonance. And in doing so, then it can potentially take these electrons from here and put them there and put an O minus. So an O minus up here, phosphorus plus. We know because of this resonance structure here that the C does have electrons to share. So when we put an electron withdrawing group here, we actually entice it to now become trans. Major product is E. So whereas before we went one way, now with electron withdrawing group, they are trans one another. So clearly this is driven more by a electron overlap in the transition state issue than it is actually with steric hindrance. Okay, so that was good to know. So next one they looked at things that are ambiguous. So this benzene ring can't interact with pi bond. So because this carbon is negative, can be electron withdrawing, but it also in theory could be electron donating, although putting a negative on the phosphorus isn't likely, but it's not a truly electron withdrawing group. It's can go either way, but it still played a role when you have that electron overlap. When it can accept electron density, it ends up again creating a scenario where you will get the two bulky groups opposite one another. So again, you get the E product. Okay, so we don't know exactly why, but we do know that if there is no resonance possibility of the negative charge on carbon to the rest of the structure, Z is your most likely product. When there is resonance, withdrawing in this case, and the potential to withdraw. So I'm going to put it as EWG, but small letters because it is withdrawing in this case. But phenols can go either way, but still you have some resonance overlap. You still get the E. So along came a whole slew of other people to study this, including Horner, Wadsworth, Emmons. So they concluded that having a resonance stabilized Wittig reagent, so whereas in the previous example, we made the carbonyl part of the reaction, the one that had the electron withdrawing group, they put it on the actual phosphoylide. They put it on this compound. So withdrawing group there. And in doing so, it took the negative charge and moved over here so that you had the phosphorus now carrying a true positive charge. The true positive charge makes it more desirable to oxygen in that transition state. So when it reacts with the oxygen in some ketone, sorry, there is a much bigger driving force for that push right there. So the alignment becomes more, I guess, stabilized. Um, this was just observed by, just in general, various research projects. So Horner, Wadsworth, and Emmons said, well, let's just overdo this. Let's not only put a withdrawing group here, not sure why they went to from ET to ME, could very well have just been something as simple as cost effectiveness or just something that was laying around lab. And they took the phosphorus, instead of having phenyl groups that could donate through resonance, but ambiguous resonance, if you will, could be donating or withdrawing. They put two distinct donators, lone pairs on O can donate in, and a distinct withdrawing group, double bond to O. So every atom now has a, I guess, better ability to resonate with phosphorus than the phenols. The phenols could, and it was important. They noticed that it had to be triphenylphosphine. You have to have the ability to stabilize plus and minus charge through resonance. But this reagent they used, and lo and behold, they were able to start getting very distinct trans stereochemistry coming out of this. And then if you can convert your ester into whatever else you wanted, then you actually had a pretty useful reaction going on. But when they used this reagent, they got a very clean, predictable, and much, I guess, faster at lower temperature reaction coming out of this because they started designing their molecule. So going back to one of the things I said right at the start of the podcast is as we got more and more into synthetically useful reactions, there were more and more people who made modifications to get what they wanted. So their goal was to get the trans species. And so they found ways to do it not through steric hindrance, but through stabilization of the phosphine in the beginning, and I guess the reactant phosphine in the phosphoylide. So they just controlled the distribution of electrons. Okay, so some examples. Let's see how we do. Standard Wittig, not a withdrawing group at all. Carbonyl here, bulky group, small group, bulky group, small group. So we will predict that you will get, with no facilitation by having donating groups here, 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 anywhere, that we will end up with the two bulky groups on the same side. So we end up with Z, because no pi stabilization at all in the transition state. Okay, we go to the next one. Again, same story. No donating withdrawing groups, no empty p orbitals to deal with here or here. Symmetric, so ends up, this one's kind of pointless. We just added across. End up, it didn't matter what way I did it because there's no stereochemistry to concern ourselves with, no E or Z. So because of that, I don't care. Then we'll look at this one, where this one is a little bit trickier. So when I look at this, you will note here is my ketone, and it has a lactone functionality on the rest of the structure. So this is an electron withdrawing group on this structure here, but it's not quite to the same extent. This O can't donate in or withdraw. It can only interact here. Still, we have that carbonyl to consider. On the phospholipid, we have just an R group, with it happens to have an alkene that we're going to react with later, and an H. So it ends up this carbon, and I should make note that there's an H here, an H here. So we're not quite to the state of our phospholipid. This is making it. You remember tubutyl lithium, bully, remove the H and then made that species. Once we make that species, then it's free to react with this carbonyl right here. So these are the two groups I'm concerned with. And on the other side, an H, that group. So because of a no real, I guess, true donating group, although this is carbonyl and it could donate, it's not positioned the right way to do so. It just acts like an ordinary bulky R group. So we know that there is no real facilitated alignment, so we end up with the cis H's and therefore the cis bulky group. So we end up with Z again. So we didn't use any of the specialty reagents. We just used boring run-of-the-mill R groups with no withdrawing nature. On this structure, we didn't have the withdrawing lined up the right way, so it behaved just like a normal Wittig reaction. All these carry some synthetic utility. So when you start looking at the structure, we have 1, 2, 3 different functional groups that we're free to react with and convert into other compounds. So when you start seeing things that are this complicated, it's usually because you're setting yourself up to do future reactions. So that covers the Wittig and the Wölff-Kishner. The Wölff-Kishner, again, just reducing a carbonyl to an alkane. The Wittig, much more complex reaction. Want you to just know the real basics, that you're dealing with a phospholipid in either an aldehyde or a ketone as the carbonyl reactant, and that if you have any sort of facilitation of the charge distribution, some sort of resonance in your phospholipid, then you have a greater potential to get the trans or the E geometric isomer as opposed to the Z. So that covers what we're doing. So this podcast all done, and we'll see you at the next podcast. Bye.